Okay, we're in chapter 7, and there we go.
You still want this?
No, we just throw it away. No. Yeah, I want it.
I don't know. I emailed you all the answers.
Otherwise, I'll forget to put your grade in the grade book without it.
Oh.
All right, so how come that says chapter 6 on top? Anybody know? Okay, now we're in chapter 7. Sampling and sampling distribution. So clearly it's a pain in the rear end to sample 100,000 people. So you want to do, you don't want to do everybody, you want to do some sampling, and with that there'll be some distribution and some errors brought in. So selecting our sample, clearly if we want some answer and we want the answer to be what we want it to be, we only sample people like us. That would be a reasonable thing to do. So ask yourself the same question 10 times and get the right answer. There's an estimation point associated with the sampling. There's distributions associated with the sampling. And we're going to have a new set of symbols. So our sampling distribution is going to be X bar. And our sampling of P bar, whatever P is, I'm sure we'll get to that. And there's other sampling methods too. So I'm going to collect data. We'll collect data on how many dollar bills you have in your pocketbook or wallet. That would be an element. We'll go out and sample 10 people in the hallway, and from that we'll know everything that we need to know about how many dollar bills you have. No, probably not. A population is a collection of those elements. So each element is how many dollar bills, population is all of them. Sample is a subset of the population. So we're going to do all Buena Vista students is the population, but we're going to sample some small set of them. Sample population, the population from which I draw the sample. Then I have a frame, a list of elements that the sample will be selected from. Okay, so all Buena Vista students could be represented by the screen. The ones at the Council Bluffs campus is just one little triangle. That'd be the frame, the little triangle. But I'm thinking about all of them. The reason we select a sample to collect the data is because that cuts down our cost. If we can cut down our cost, that's a good thing. Sample results, only estimates. Okay, so I'm going to sample who's voting for the President of the United States. That's only an estimate. It's good, plus or minus some percentage. The reason is simple, because our populations are normally big. And now we have to use good sampling measures. So if I'm pro guns, then I'm going to sample only people who are IRA card holders to find my answer to the question, right? And if I'm anti-gun, I'm going to reject anybody with a, well, that would not be a proper sampling method. That would not give me a good estimate of the characteristic. I got to have a cross section of the population. I can't just pick from my friends. We have a finite population in the United States. What's that, about 300 million or so? We could be sampling from an infinite population. Anything infinite that you know of? Let's see, stars in the galaxy, 10 to the 11th. Galaxies in the universe, 10 to the 11th. Those don't sound like infinite numbers, do they? But if we tried to, all the temperatures between 0 and 100, then that would be an infinite population, because I can make those digits go on forever. So I have a membership list, I got a credit card account number, I have inventory of product numbers. So I got some finite population that I'm sampling from. My size is going to be N, and big N, and my sample size is going to be little n. And we want that little n sample to have the same probability of distribution as the big N sample would have had. That's the whole purpose. So we're going to replace each sampled element before selecting subsequent ones. Alright, sampling without replacement. So I have a bag of marbles, and one of them is black, and 50 of them are red. I can sample and pull out one, and then I can sample another one without putting the other one back in. Or I can sample the first guy, put him back in the bag, and then sample again. So that sampling with replacement, putting it back in the sample, sampling without replacement. So if I'm trying to figure out well, who's voting for the president, I don't want to call the same guy twice. Because if I do, I'm just going to get a different answer, right? Because we all lie to those people, right? Don't we? We pick up the phone, and they want to know something, and we just play to their strengths and lie to them. In large sample projects, computer-generated random numbers are used to pick out the samples. St. Andrews College, 900 applicants, so I got a finite group, admissions. We number 1 to 90, and we select a sample of 30 of the applicants to find out something. Do they have enough money to be here? Whatever it is we need to find out. Assign a random number to everybody. Random number generators normally get between 0 and 1, and Excel has one of them. That's fine. I don't think my calculator has a random number generator. Yes, it does. My calculator does, in fact, have a random number generator. So if I go second function, random number, I'm going to put something in there, enter, and I get an error. So obviously I don't know how to use my random number generator, but I do have one. And a random number generator is going to be a constant between 0 and 1, how it's going to be distributed. So I give them random numbers. Sometimes we want to do, we have an infinite population. We don't know how many people are in the list. What are we going to do? We can't construct a frame of the population. So we can't construct a random number selection procedure. So what are we going to do? Tell me what we're going to do. So we do an ongoing process. No upper limit on the number of units that can be generated. Okay. Fine. Parts being manufactured on an assembly line. Whatever. Transactions occurring at your bank. Telephone calls arriving. Customers entering a store. So we probably don't remember the dentist. We probably don't remember the dentist and dentist store where the drugstore was going to give a 5-minute free shopping spree to the 50,000th customer, or some number of customers, and Mr. Wilson had figured out exactly when that was going to occur, and he was in the line at the right spot, and at the last minute he redid the calculation, found out he was one shy, and sent Dennis in before him, and Dennis turned out to be the customer. Remember that, Dennis the Menace? Had to be, some of us are shaking. The older people in the group are shaking our head, yes, we remember that one. The younger ones said, who's Dennis the Menace? And it all turned out good because Mr. Wilson had already figured out where all the good things were that he wanted, and he was going to get them. And then he was hosed over. We just got monitored by the boss out there, by the way. But the drugstore had taken all the good stuff and put it high up on all the shelves. But because Dennis had gone through the line and was the person, he could climb up the shelves and get it off. So if we don't remember that one, then that's just the way it is. Customers entering a store. Sampling from a finite population. You must select a random sample from an infinite population. Otherwise, we've hosed ourselves over. So I can't sample everyone who has their name starting with A. That won't work. Okay. Random sample. We have to come up with what those conditions are. And each element needs to be selected independently. Now who are they? The Gallup people on the other side of the river have huge computer systems over there doing that. And their computers are all 1G networked together, and it's really cool, and they can do 1,000 calls a second, and they can figure that out. Point estimation is a statistical inference. You use the data from a sample to compute a value that serves our particular interest. So it might be the mean, it might be the mode, it might be whatever, but be a point estimation. We refer to X bar as the point estimator for the population mean mu. Okay? So we don't know what mu is. We don't know what the mean is. We can't figure it out. It's an infinite number of people. So we come an estimator, X bar, that we can figure out. I sample 10 spots. I come up with 10 numbers. I'm going to use X bar for that. And I say that's my estimator for mu. Point estimator for the standard deviation, S, is going to be used for, instead of sigma, little sigma, for the standard deviation. P bar is the point estimation for the population proportion P. Okay, so I don't know what it is, but I can go and figure out what it is. Okay, so I've got 900 people, and I have SAT scores, and whether or not they want or don't want to be in housing. A meeting a few hours. The director of admission would like to announce the average SAT score for my applicants, and I don't have time to add up all 900 of them. Of course I do. It's in the computer. I just have to do just put, give me a break, guys. The data is there. I can get it out. I have 30 staff members that could get that piece of data out. But no, I got to do it by hand. The necessary data on the applications have not yet been entered. Wouldn't you know it? In a computerized database. Fire my director of admissions. So we're going to estimate the population by sampling 30 of them. Okay, that's fine. So I add up those 30, divide by 30, my estimate of the mean for the SAT score, 1097. Is that good or bad? Is that an okay number? Is that a number higher or lower than Iowa State? Higher or lower than Buena Vista? You guys wouldn't know, right? Because you didn't need to have to take the test to get in. So, my first daughter had 1,200. That was good enough to get into Penn State main campus. So, 1097 is probably okay. That would not be the average number at the Coast Guard Academy. That would be closer to 1350 at the Coast Guard Academy for their applicants. All right. So now we're going to come up with the standard deviation. We're going to do a point estimation. We're going to do the same standard deviation we did before. We're just going to call it S because we didn't do it on all 900 people. Okay, so it's the same sigma we had before, the same calculation. That's n minus 1 sitting there, 30 minus 1 on the bottom for 29. We're just going to call it S because we didn't do it for the whole population. And what the heck is this? How do they get 20 divided by 30? I have no idea how they got 20 divided by 30. Oh well, maybe they'll tell us later on. But I can go and take that same set of data, sample it differently, get different numbers. Perfectly okay. I don't care. So once we've added them all into the calculation, we can do other things. And we find that we really have a 1090, and we really have an 80 for the standard deviation. Oh, that's the people that wanted to be in housing. That's what that was. So 648 out of 900 wanted to be in housing. Instead of 20 out of 30. So we based decisions on data that was wrong, but data that was perfectly okay within anybody's idea of correctness anyway. Summation. Parameter value, point estimate, real value, point estimate, and who wanted to be in housing. So the glorious people at Iowa Western spent last week, oh, enrollment is down. We don't have enough money. We're going to have to cut the budget. Quick, go look at your budget items to see what you can cut. And what came across today? Well, we recalculated. Enrollment's down 0.6%. Forget it. We don't have to cut our budgets. So the first thought was, the first cut was something's wrong. But when we went back and looked at all the data, the high schools saved us. So the arts and science people on the main campus are down 1,000 student credits, but the high schools are up 900 student credits, and there's only 0.6 difference between what we thought we were going to have and what we really do. But we write our budget based on a 5% increase of students every year. Is that realistic? Not forever. Sometime it has to go down, right? Yeah. Target population, probably want to make inferences about. Sample population, what I actually did. And we have to make sure the sample population closely relates the characteristics of the real thing. All right. Statistical inference. We have a mean. We do a random sample of n things collected. That gives us a estimate of the mean. And then we use that estimate of the mean to make some decision. Make some inference about what we're going to do, whatever it might be. So I have some expected value of the population. So the sampling distribution, X bar, should be the expected value. The expected value of X bar should be mu if I'm unbiased in when I took the data. If I bias the data one way or the other, then I'm cruising for trouble in my answer. Standard deviation of X bar. And population, okay. So standard deviation of X bar, whatever the standard deviation of the infinite population is divided by the square root of n, that's fine. Oh, looks like we're cruising for a whole lot of math here, doesn't it? What is it that we know? Well, we know the capital N, probably the size of the population. We know little n, what we're sampling. But which of these guys do we know? Looks like I have one equation, two unknowns. The standard error of the mean. Oh well. We'll cross that bridge as soon as we get the homework problems, right? When the population has a normal distribution, the sampling distribution of X bar is also normally distributed. Oh, let's hope so. So as long as my sample size is 30 or bigger, if I have a normal distribution in the general population, my sampling distribution will also be normal. Isn't that nice? If I'm slightly skewed and I have outliers present, then I'm going to need at least 50 samples before I can say that. Okay, so I added my children in, and they're way over there on the left someplace because they didn't bother to graduate from 8th grade. Sampling distribution of X bar. The sampling distribution can be used to provide the probability information about the sampled mean. Okay, I guess we can do that. Central limit theorem. Now, as I recall, the central limit theorem was not something we have seen in any slide so far. When the population, which is selected at random, does not have a normal distribution, the central limit theorem is helpful in identifying the shape of the distribution. Oh, here we go. Central limit, in selecting random samples of size n from a population, the sampling distribution the sample mean can be approximated by the normal distribution if the size becomes large. Oh yeah, exactly. If I have a large enough sample, everything will be fine in my life. So I come back to St. Andrews College and I look at the SAT data, and I see that my expected value of 1090 was the mean, so that's good. What's the probability of the sampling? The sampled random distribution score will be within 10 of the mean. Oh, okay. Calculate the z-values at the upper end. There's my z-values. Find the area under the curve to the left of the upper limit. Isn't that nice? So you go back to z-values. Cumulative probabilities of the standard normal distributions. All right. Z-value 0.68 gives me 0.757. Time to open the back of my book again. St. Andrews College. Sampling distribution of the SAT scores. Right? 1100, the area that side of 1100. Calculate the z-value at the lower endpoint of the internal interval. The lower endpoint. Okay, so we're looking at plus or minus 10%. So we calculated the plus or minus 10. We calculated at the top end. Now we're looking at the lower end, and the probability of being at the lower end, 0.248. And I would imagine we're going to subtract those two. What do you think? So that's that probability. So we want to have the probability between 1080 and 1100. We're going to take the 1100 guy, subtract this area from it, and come up with that probability. I can just see it now. There we go. The probability of being plus or minus 10.5%. So, yes, 50% of the SAT scores are plus or minus 10 points. How many slides did it take to do that anyway? One too many. What are we doing now? Oh, we're just throwing the same thing over again. Suppose we select a random sampling of 100 applicants instead of 30. What's going to happen? Our expected value remains the same. However, we have only on 8, our standard deviation is only going to be 8 away from the mean instead of the 14.6. We have a better curve. I got a better curve because I sampled 100 things. And now I'm asking the same question, plus or minus 10. Or plus, or is it? Right, plus or minus 10, samples 100. Now I have 0.788. I have a different probability of being right, basically, based on my higher sample that I have. Because the sample distribution was 100, has a smaller standard deviation, the value x bar has less variability, and therefore that's my situation. Okay, and now we see we have a different curve in a different area from the same data. Isn't that lovely? So whoever said that we couldn't lie about this, right? Didn't we say that statistics are, well, who said it? 90% of statistics are made up when the guy's talking about it? Who said that? Anybody know who said that? I think that was Chris Conrad over in Lewis Hall. I think that was, yeah. Sampling distribution, making a difference about a population proposal. So, yeah. Oh, all politicians? Yeah, okay, there you go. So $16 trillion debt, that's not a problem, right? Yeah, that's only 100,000 for you, 100,000 for me. Take it out of our height now, it's all paid off. Yeah. Population with proportion. A simple sample of n elements is selected from the population. The sample provides a sample proportion, and we make an inference back to what that is. So in the case of, am I in the dorm or not? Yes or no? That's what we're talking about. Just a yes or no thing. Expected value. Expected value of a yes or no question would be yes or no. I guess. Yeah. Standard deviation for a finite population. Okay, I'm sure we're going to remember that equation. Got it memorized yet? And for an infinite population, that's better. I like that one better. I have some correction factor. Normal distribution wherever the sample size is great enough to satisfy it. N times P is greater than 5, and wonder what that means. Well, 70% of the prospective students applying desire on-campus housing. What is the probability that a single random sample of 30 applicants will provide an estimate of the population proportion desired on-campus housing within plus or minus 0.05 of the actual population proportion? Well, at least the question was written in English, right? So N is 30, P is 0.72, normal distribution, blah, blah, blah. We want N times P is that which is greater than 5, so that's good. And we do the other calculation, and it's greater than 5. So we can now say that this will satisfy a normal curve, because both of those numbers are greater than 5. We can calculate the sigma, 0.028. Okay, and what do we want? We wanted, I forget, but I'm sure it's going to tell me pretty soon. So now we're going to find the upper z value, 0.61. So plus or minus 0.05, right? So that's the mean. 0.05 more is that guy divided by, where did that guy come from?
What was on the last page?
Yeah, forgot already, right? All right, we'll move back. Gotta move back further. One more? One more. Oh, that's the standard deviation, right. All right, standard deviation of population. Okay, so we found the upper zebra value, and now we're going to find the area under the curve to the left of the upper z value, and that's going to give us a probability off our z chart. And then we're going to do it again. Okay, no, we're not. We're just going to see where we got it off our z chart. And then we're going to do it again. Now we're going to see what it is. Okay. Then we're going to calculate the lower z value. So minus 0.05 from the mean gives me that. I have that divided by this. How come this is not? Oh, it is a negative number. I see it right there. So with a negative number, I come up with the probability off my z chart again. There's the probability area there. We subtract the 2. So there I am subtracting the 2. And there we go. 0.45. And I forget what we're trying to calculate. Oh, plus or minus 0.05. The probability that we want to have housing. Isn't that lovely? Are we going to do it again? Oh no, we're just going to show it again. All right. One more time. Other sampling methods. Stratified random sampling. Okay, so I go to the muddiest area possible and sample around there. Cluster sampling. Systematic sampling. So you're watching the History Channel, and you're watching a World War II show on the History Channel, and they're showing you bombs falling out of planes, hitting things. What are they hitting? Orchards and farmland, right?
Industrial settings?
Nah, they miss those things all the time. They get the hospitals, the schools, and they get the orchards and the farmland. Yeah, that's what they get. Because our average bomb dropped a mile away from its target and missed. So in order to get a target, get a bomb on the target, we had to drop 100,000 of them to get a couple where we wanted them to be. You know, same type of thing. Cluster sampling. Systematic sampling. Convenience sampling. Judgment sampling. Now, what's the difference between judgment and convenience? Come on, guys. You gonna have to do better than that. So, stratified sampling, we divide the groups into elements called strata. The top 10%, the bottom 10%, the middle 50%, and each element in the population belongs to one or more of the strata, one and only one. And then we sample out of those groups. So we get something from each stratum. Okay, so if I'm going to take 10 sample points, then I make up every 10%, and I take one sample point out of each of the 10% guys. Stratified. A simple random sample is taken from each stratum. And we can, computers will have formulas to figure out which one that is. And this, as precise as our stratums are. All right. Cluster. The population is divided into separate groups of elements called clusters. All right. Well, and we take samples out of the cluster. Okay, that's good. All right. Cluster sample. Primary application in area sampling where clusters are city blocks or other well-defined areas. So I take a city block here, a city block there. Close proximities of elements can cause cost effective disadvantage. So we did that during the snowstorm in Connecticut. Everyone got the same 42 inches, even though some only got 30 and some got less than 42. Everybody got 42 because that's what the guy that got the most did, right? Systematic. The sample size n is desired, contained from n elements, and we might sample one element for every n divided by n elements in the population. We randomly select one element first from the population list. And then we select every n divided by nth element following on the population list. So if I have to have a population list to begin with to do systematic I, if I can do that, all the voters in Potawatomi County, that's both of them, right? So that'd be a pretty short list. No? For the longest time, Iowa Western was unable to get a bond issue passed. The last two bond issue passed. How come? What's the difference? Well, before, we were putting the bond issue during a general election when everybody was showing up to vote for the president. And when you do that, everyone shows up and they see this stupid issue on there saying, I want more money, and they vote no. Right? The consultants told us, don't do that anymore. That's dumb. Make the bond issue the only thing on the ballot. Okay, so now we have a bond issue where the only thing on the ballot is the bond issue. We hold it in December when there's going to be snow, and no one can come to the polls to vote on it. Okay, that's good. You put together a call list of all your graduates and alumni and family friends of them, and you call them and you ask them the question, are you for this bond issue? When they say yes, you send them an absentee ballot. When they say no, you say thank you very much and hang up the phone, go to the next person. The last two bond issues, there were 10,000 votes cast. 9,000 of those were absentee ballots. Supermajority is required. 50% doesn't count. You have to have 60% on a bond issue. Are there more than 10,000 voters in Area 13, the 7 counties that have Iowa Western, 150 miles each way, 50 miles to the east? Yeah. Did it really matter? No. Because why? $20 million across that, a size of Iowa, the size of the state of Connecticut, is not a whole lot of money per individual household. It's less than $1. So, the method of probability. Advantage, systematic. Sample is easier to identify who we're going to sample. Selecting every 100th person on the list in the telephone book. Is that going to work? Yeah, probably. Yeah. Unless you have a short telephone list, then it might not. Convenience sampling, non-probability sampling technique. Items are included in the sample without known probability of being selected. So I do whatever I want. It's convenient for me to do that. So I use student volunteers as my sampling. Okay, those that would like to volunteer, you're going to take this survey for me. Those guys that don't, that's okay. You can go home early. Who gets here? Who stays to do the survey? The 2 or 3 brown nosers in the class. The rest of you go away, right? Do I get the result I want? Maybe, maybe not. But it's convenient, right? Doesn't cost much money. Selection data are easily done. Disadvantage, it's impossible to determine how representative the sample is. Judgment sampling. I am so knowledgeable of the area, I'm just going to use my feelings and get the right people here in the population, and that's going to be good enough. Don't you think that's good enough? And from that, we're going to solve all the problems. We're going to study the issues that way. It's non-probability sampling technique, and I'm right. So a reporter decides to sample 3 or 4 senators. Yeah. And that has to be the general opinion of the Senate. Are there 4 senators that have the same opinion of anything in the Senate today? Well, maybe. They have, on the length of a traffic light being red. I'd probably have an opinion on that. Might be the same. Advantage, easy to do, and I get the results I want, right? Disadvantage. So I'm doing a program evaluation of my program, and I need my advisory board to answer a questionnaire. So I email it out to them. The ones that answer it, fine. The ones that don't, fine. Who cares, right? The quality of the samples will depend on the judgment of the person selecting the samples. Oh, bummer if that's me. Okay, recommendation. It is recommended that a probability sampling method, random stratified cluster systematic, be used. Aye. How much good is it? So I can't judge on goodness if I do a convenience or a judgment thing, but I can judge on goodness if I do a random stratified whatever. We're done with chapter 7. Isn't that lovely? Now, can we do the homework problems in chapter 7? That's the next issue. No.
I said good.
We're done goofing off. And now we're going to do chapter 7, number 5. Anybody want to read the problem?
Student government organization is interested in estimating the proportion of students who favor a mandatory pass-fail grading policy for elective courses. A list of names and addresses of the 645 students enrolled during the current quarter is available from the registrar's office. Using 3-digit random numbers in a row 10 of table 7.1 and moving across the row from left to right, identify the first 10 students who would be selected using simple random sampling. The 3-digit random numbers begin with 816, 283, and 610.
Okay, now that we've agreed that the question is written in English, we need to find table 7.1. Okay. I found table 7.1. 3-digit random numbers. The 3-digit random numbers begin with that.
Oh,
Good, I guess I did it.
All right. So these are random numbers. Excellent. All right, so let's see. We have to find 6, 861, and 283, and 610. 616. So that's what we're looking for.
by one.
Row 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I see 6, 8, 6, 1. Where is this?
What am I supposed to do right now?
That's what I did.
Okay, where's this 283?
They're all in a row.
They're in that row? Going down? Oh, they're
No,
not.
they're not all in that row. Because I found the 283 in the last column, second number down.
Are we on table 7-1?
I'm looking at table 7.1 on page 269.
Yeah.
Okay,
6, 283, 610.
the question is, where is 283?
It's
Last
To
column,
the-
second one.
last column to the right, second one down
Find 16.
Please do, that's the only one I cannot find.
from the top.
Oh, what?
To the very right,
Okay, I found it. Alright, so we found that number. Can you find 610?
No, that's the only one I can't find.
601.
610.
613.
What do we get?
Free pass.
Look at the game. That's kind of funny, I know.
Yeah, with trifocals, this makes it very difficult.
Right where 816 is, if you keep going across,
Yeah,
and if you're reading it across, it says 816, 283, 610. Is that not what we're looking for?
Right?
I don't think so.
What is it doing now?
It's the first 3 digits.
It's the first 3 digits that we're looking for.
Okay.
All over that table.
Yeah.
Because they're not in the same row or the same column anywhere.
Okay.
It's just the first 3 digits of that little set.
Yep. 716.
Alright, back to the question.
that's the case, then why is there not? a 610?
Identify,
You can't find it either?
No, it's not in there.
I didn't
I
think so.
don't think.
Yeah,
I
I
went
can't
through
find it
everywhere.
Three-digit random number.
The closest I could find was 160.
okay. Okay, this is what we're gonna do. We're gonna start with the first number. Okay? Gonna do it first. And it says 3-digit number, row 10, and move across from left to right. Okay, so what we're gonna do is gonna take that guy, then 361, then 392, then 568, then 376, and we need 10 of them. 1, 2, 3, 4, 5, 24, 980, 896, 649, 993. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we have, that would be one sample set. One random sample set. And then we're going to take another random sample set, starting with number 283. So we're going to start with 283. And we decided that that's,
But it says only three of the
say again?
And in the problem, it instructs you to use line 10.
Yeah.
So I would assume
You would use it for everything.
Yeah, but where is 283 in line 10?
Not.
It's
So,
not.
but in the
That's the-
problem, it does say that in row 10 of table.
it's not saying, I mean, the way it's worded, it's not saying that you start out, that when you look for that 3-digit random number, you start out in the first number on the left of the column. That's not what it's instructing. It's instructing you to find that number in column 10. It's not saying that number is going to be the first number in the set of 5 numbers.
Like 610 is in that second set, right? In the middle.
Because the numbers being organized into groups of 5 is just to make it easier. That has nothing to do with the problem at all.
That's someone understands this.
I don't know. I thought this.
Glad you understand this.
I thought this was.
Well, I mean, because it's not asking you to look for those 3 digits as the first 3 numbers. The question says to look in line 10. So line 10 is that 816. And so it's asking you to find for the 3, when you're trying to identify the first 10 students who'd be selected using simple random sampling, use those 3 digits in line 10. So I would assume that the first time for the first student we use 816 and start from there, and the next one we stay in line 10 and start with 283.
And then 610,
For-
039.
Why do you go from 610? Yeah, he's right. Look at that. All the way to 164. All right. We don't need this number. I don't know why I wrote it down, but I think.
Okay. So, recapping. We're only doing it once. And we're not doing this. And the guy that start with 616, 861, the guy with 861, we're gonna call him 283. I don't see how I get 283 out of him
It's
though.
the next three digits
Next
after
three
816.
digits.
Oh,
Oh, okay.
Oh,
Now I got it.
okay, okay, yeah, alright. So I'm starting with 613, but I'm not using it. I'm using 283, then I'm using 610, and then I'm using 039 and 254. So I'm using all the digits that are there. 5, 6, 8, 3, 5, 3, 7, 6, 3, 6, 0, 2. Do I have 10 yet? 1, 2, 3, 4, 5, 6, 7, 8. 2 more.
421.
0, 2, 4, 2, 1, 980. And we do a quick look at the key. That's not what we have.
No, we have it all.
Nope.
What did we?
610.
Wait, hold on, leave it
Hold
up
on,
there.
hold on.
We messed up at the 353.
353? So I got 353 right.
Yeah, and then after that, what did we do? I don't know.
That
They had
602 needs to be next.
So for some reason it's.
353.
Yeah, skip
I show a 7, 6, 3 next.
Yeah, but they still said they have no.
602. So we'll allow it that they messed up. All right. Now,
Will you go back just so we can just see what
View.
they had? Maybe we can figure it out.
zoom.
So why are we
70
starting
there.
with
So there. Now we can see them all.
That part I don't understand.
So we got that guy 603, 39, that guy 568, 353, but 353. Yeah, they skipped one.
Yeah, that's just the error.
Yeah, they skipped one. Thank
Oh,
you.
and then they skipped
They're probably
980.
using
Yeah.
That 429 should be
429.
241.
Yeah.
421.
So probably you're probably right. The key is probably a previous edition of the book, and no one bothered to make the key right.
Right, but that 429 that you wrote down should be a 421, shouldn't it?
Yeah, it is.
Yeah, it's supposed to be 421. Well, I go down. Right
4,
there.
2, 1.
Yeah, it should be 421.
Okay.
So you want us to write down what you wrote, or?
Doesn't matter. Yeah, what I wrote. Yeah, because that's how we got it. We started where it said to start, and we used 3-digit random digits across there.
I don't
Yeah.
get this.
So why are we doing that? Well, we're doing that so that these are the students that we sample. That's why we're doing it. We're
Okay.
finding random numbers of students to sample from a random number table. Randomly.
Random.
That they're five.
No.
They're random.
Got it.
What she was asking was
Why they put it?
why they put them in groups of 5.
I think that's just so you can look at it.
Yes, yeah.
Yeah,
So it's just not all a bunch of continuous numbers.
anyway.
Which is absolutely right. Back in the days of Fortran programming, what would your printout look like? And it would look like that. Groups of 5s with spaces in between.
Okay.
So in the days of current programming where we don't use formatting like that, like they did in Fortran, then we wouldn't have it that way. We'd have it differently.
Okay.
Got it.
Excellent. Number 11. One down.
11%.
The following data has been sampled randomly. 5, 8, 10, 7, 10, 14. What is the population mean? Okay, so X bar, summation of the X's divided by 1, 2, 3, 4, 5, 6. 6 of them? All right. um, 10, 20, 30, 40, 52. 52 over 6?
That's what you do.
Eight and 2/3.
Yeah, yeah, well, I got 54 too.
Hmm?
And that's what we're doing.
You got 54? You mean I can't add them in my head effectively? Is that what you're trying to tell me?
Oh, no.
Yeah, I got 50. I got 54.
And so 52 divided by 6, right?
Actually, we use 12.
That's 9. I was gonna say, I'm not very good at fractions. I know it's 6 but I don't know if that's 2/3.
Point 6666. Yeah, but it's not that anymore because now we're dividing
Why
by.
did we do 2/3?
Now we got 9. What is the population standard deviation?
Yes.
Okay, so now we want to take summation of the xi's minus the x bars squared divided by n minus 1. So that's what we're doing. And that's going to be, okay,
When should we be?
9.
Oh, nothing.
All right, so 5, and then we got to take the square root of the whole thing, right? Square root of the whole thing. All right, so 5 minus 4. So that's 4 squared plus 1 squared plus 1 squared plus 2 squared plus 1 squared plus 4, 5 plus 5 squared divided by 5, and then the square root of the whole thing. Well, the mean is 9, so I'm looking at each of the sample points. Between 5 and 9, the difference is 4. Between 8 and 9, the difference is 1. Between 10 and 9, the difference is 1. Between 7 and 9, the difference is 2. Between 10 and 9, the difference is 1. Between 14 and 9, the difference is 5. Now, I could have just put it in my table and had it do it that way, too. I mean, I don't have to do it this way. So 16 plus 1 plus 1 plus 4 plus 1 plus 25 equals, divided by 5 equals, and then I want the square root of that. 3.1? And I look down on number 11, and I see a 3.1, and I see a 9. View, zoom. That didn't zoom much, did it? View, zoom. That didn't zoom much either. Oh, I can't see it all. Bummer. Oh, I know. Never mind. I got it. Got it figured out. Okay. And that's exactly what we did. So, 2 down. Looking at 17 next. Can I do something? What would you like me to do? How about that? We'll do that. I found 17. The American Association of Individual Investors polls subscribers on a weekly basis to determine the number of bull and bears or neutrals on short-term prospects for the stock market. For the finding for the week of 2 March are blah, blah. Bullish, neutral, bearish. Develop a point estimate for the following population parameters. Okay. The population, the proportion of all subscribers who are bullish on the stock market. The proportion who are bullish. Let's see. I would say our total number 409 plus 299 plus 291. So we'll get a 409, 299, 291. 999, really?
Karina was in
Did I do that right?
Yes.
Yeah, 999. Okay, so A, we want bullish. Okay, so bullish would be 409 divided by 999. And B is neutral, 299 divided by 999. And C is bearish, 291 divided by 999. Okay, that's good. Now we put it in our calculator. 209 divided by 999. Oh, I think 0.41 would be good enough. What do you think?
Yep.
And probably 0.30. 0.29, and they all add up to 1 when I get them added up to 1. So that's problem 11. We'll see what the author thinks. That's problem 17. We'll see what the author thinks. Oh, look at that. The author even carried the same significant digits we did. That's
Will you put that question on the bottom?
that is so disgusting.
How come,
Will you put that question on the text?
I don't see how, but
how come you round it up on B, but you round it down on C?
I'd have to look at them again. Yeah, you know what it is? This guy here is 0.9, 0.291.
It's the third significant figure
Yeah.
in the
Yeah.
291.
Yeah. So it was a 1, that's why I got rid of it.
Yeah.
But it was 0.29 something.
It was like 0.299
Yeah.
or something.
Yeah. So it would appear that we're perfectly happy with chapter 7, and when the whole final should be on chapter 7.
Yeah, I'm doing pretty good on this one, so I'm good. I'll take 17 and 5 on that for sure.
Number 23.
And if you could leave chapter 6 out of the test completely.
That would be good.
6
Yeah.
and 5.
You should probably send an email to that effect so that we can have it in writing that you want that way. Where was I? 20. Okay, I found 23. In the AIE sample of sampling problem, see figure 7.5. Okay, I'm looking at figure 7.5. We show that N is 30. Now, where do we show that? Oh, there it is. N is 30, I see it. There was 0.503 probability of the sampling having a mean within plus or minus 500% mean population. Okay, I see that too. Okay, that's good. All right. What is the probability that X bar is within $500 of the mean, population mean, if the sample size used was 60? Okay. Okay.
That's not true.
Hmm? All right.
When you become a teacher, do you get to choose what classes you want to teach? Just curious.
Let me
Or do you
think.
like statistics?
Let me think. This is a, wait a minute.
Okay.
What?
Hmm?
What?
23.
Okay.
All right,
Who's on second?
Yeah. So the
Wow.
issue is,
who's on third?
What's on first?
Exactly.
what? We want to find X sub whatever is bar, which is the sigma guy divided by the square root of the n guy. All right, so that's what we're doing. We have a the mean. Now that's sample population was shown. Okay. So this is going to be 4,000 divided by the square root of 60 instead of 4,000 divided by the square root of 30 because we changed our sample size. All right, so 4,000 divided by square root of 60 . 516.4. 516.4. Alright, so now we know the sigma. What is the probability that we're going to be within 500? Okay, so we want the z value. The z value. Right. So I'm looking for the upper z value. Five to 300 minus 51800. So the mean is 51800. I want 500 higher than that, divided by the standard deviation 516.4. So there's the upper z value, and then we want the lower z value. 500 less than that. 51300 minus 51800 divided by 516.4. Okay, so 500 divided by 516.4 equals 0.968 minus 0.968.
Is it supposed to be 51, 300, and not 52?
The upper one is 52,300. The lower one is 52,300. Okay. Now we got to find the probability of the upper z guy, the probability of the lower z guy, and then we're gonna subtract those two guys. All right, so I'm heading towards my table in the back of the book, which I don't really remember where he is.
605.
605. 605. And I have a 0.961, 0.96. I can have a 0.96, or I can have a 0.97, and that's as best I can do. So I'll go with 0.97, 0.834, and the lower Z value minus 0.97, 0.166, 0.166. So the probability that I'm between the lower Z limit and the upper Z limit, 0.834 minus 0.166, .718. So that'd be the probability that I'm plus or minus 500 when I have a sample size of 60. Okay? Well, we still have the B part. Now we have to do it again for a sample size of 120. Oh, someone's looking confused already.
I don't understand why you have 4,000 at the beginning.
The 4,000 is easy to come by because it's part of chart number 7.5, isn't it? Where is it? What table? Where am I supposed to be?
7.5 would be the table.
Yeah. On page 285. We're using 4,000. Yeah, right. On page 283. So 283, table 7.4 is where it begins, and sigma is 4,000.
Oh, that is the 30, okay.
So when we did it with the 30, we did it with 4,000. When we did it with the 60, we're going to do it with 4,000. We don't have a choice.
Doesn't say anything else. Yeah, this is very misleading.
Yeah, isn't that nice of them to just help us out like that? Yeah. All right, now we're about ready to start part B. So part B, we're doing it all over again. We're looking for that guy. We're going to take 4,000 divided by the square root of 120. And we're going to get 365.1. Okay. Now we're going to look for an upper Z limit and a lower Z limit. And we're going to skip the stuff in the middle because it's all divided by 500. 365.1 minus 500. 365.1. $1.369. Well, why am I doing it twice for? That's stupid. I'm gonna get the same number. Alright, so I want to get the the probability of the upper z, and then I'm going to find the probability of the lower z, and then I'm going to subtract those two to find the probability in between. So that's my plan. I got to go back to, oh, I got right to the right table. So 1.369, we're going to call that a 137. 0.9147. 0.9147 minus the lower z value, minus 1.37, 0.0853, 0.0853. So the probability 0.8294. And this is problem number 23. That's not what you have?
Wrong button.
Yeah,
Six, that's what I can look.
0.8294.
0.8294.
Yeah, I definitely put in a different button.
Yeah, that's the number we got for A. And that's the number, not yet. 0.8294, is that what we got?
Where did the other number come from?
0.29, yeah, that's exactly what we have. Okay, so the bottom line is the final answer is still the same thing. Okay, that was 23, looking at 29. Hoping that it doesn't get any more difficult than that. 29. Oh, good. A, B, C, D, E, F, G. The average price of a gallon of unleaded gas was reported at $2.34 in Kentucky. Use this price as the population mean and assume the population standard deviation is 20 cents. All right, so my population mean 2.34 and the population standard deviation 0.20. Right. A. What is the probability that the mean price at 30 gas stations is plus or minus 3 cents? A. All right, so we have to calculate that guy, which is going to be 0.20 divided by the square root of 30. 0.2 divided by square root 30. 0.0365. So now we got to find the upper z. Upper z. .34 plus 0.03 divided by 0.0365. That doesn't look good. That's not right. What are we doing wrong? The difference between the mean and where we're going. Okay, That's what we're doing wrong. Well, way to go. 0.3 divided by 0.0365. Seriously. I'm still
Yeah. Me too. Point 8219.
yeah.
0.8219. Yeah.
Yeah, well,
Yeah, I just
No,
thought that.
8 point.
I 8.2.
Oh. 0.3. 0.03.
Okay.
Oh, there it
It
is.
just takes me a minute.
The problem is it's 0.03, not 0.3. It's 3 cents, not 30 cents. So 0.03 divided by 0.0365. 0.8219. And then we want the lower z minus 0.03 divided by 0.0365 minus 0.8219. Now we want the probability of the upper z, and we're going to subtract the probability of the lower z. And now we're going to go back to our z table. 605. 0.82 is the best we're going to do. So we'll go with 0.7939 minus the probability of the lower z, 0.2061. It looks like I have a 0.5878. Okay, so that's my A answer. And now I'm looking for a B answer. All right, the B problem. What is the probability if I do 50 gas stations? Okay, so I want my upper Z to be 0.03 divided by 0.2 divided by the square root of 50. And I want my lower Z to be 0.03 divided by 0.2 divided by the square root of 50.
Would that be negative?
And that'd be negative, you're right. It'd be a negative.
Would the whole thing be negative or
Yes.
just the 0.03?
Well, just the 0.03, but the answer will be negative.
I had to do this part first. On the other ones, and then I start over, and then it's really.
All right, so it looks like
It's really cool. My note really paper like this, but I'm sure that was good.
it looks like I've got 1.06 and minus 1.06, and I know we don't have those. Well, we might have points. Yeah, yeah, we have both of those. All right, so those would be okay guys to keep. Don't have to round them up. So now I want probability of upper Z minus probability of lower Z. And Travis is saying he's not getting a 1.06.
Well, I don't know if I'm doing it right on the calculator. That's all. So yeah,
0.06, 0.03. So I'm going 0.03 times the square root of 50 because I'm inverting and multiplying, dividing by divided by 0.2. Nope, that's what I'm getting. So in my calculator, I'm putting 0.03. Well, I'm inverting this and multiplying. So I'm going 50 divided by 0.02. So my calculator, I'm going to put in 0.03 times square root of 50 divided by 0.02.
in your calculator on the last question, how'd you divide the 4,000 divided by square root of 60? How'd you type that in your calculator?
Okay, so this is the problem before then.
You could use that one up there.
Alright, so I want 4,000 divided by the square root of 60. So I would put 4,000 divided by, and I would hit my second function key, my square root key, 60, and then enter, my enter key. So that's what I would do. Now you may have to put brackets around that square root.
Oh, maybe.
You may have to do that. You may not. All right, back up to the top here.
Oh.
That part's
Now I'm looking at the Z table 1.06, 0.8554,
Thank you for showing that.
and then minus 0.06, 0.1446. And then I subtract those two. .7108. So that's my final answer to B. On 29, looking at B, and 0.7108. Same thing that we got. Excellent. No use going on if we get a different answer, right? C. We're going to do a sample size of 100. Okay, so I'm going to take my upper Z, my lower Z, 0.03 divided by 0.2 divided by square root of 100, minus 0.03 divided by 0.2 divided by square root of 100. Square root of 100 is 10, right?
Right.
So this is going to be 0.3 divided by 0.2 and minus 0.3 divided by 0.2. So that looks like 1.5 and minus 1.5. If I could write minus 1.5, that is. Alright, so now I need the probability of the upper Z minus the probability of the lower Z. And 1.5 would be 0.9332, and minus 1.5 would be 0.0668. So I have a 0 point, way to go. That's such a cool one. 0.8664 for my C answer. My D answer. Which, if any sample size in parts A, B, or C, would you recommend to have at least a 90% probability that the sample mean is within 0.3 of the 3 cents of the population mean? It looks like none of them, because we're only within 50%, and then we're 70%, and then we're almost 80%. We're 86%, but nowhere do we get 95%. So I would say none of them. We need more than a bigger sample size than 100. And we'll come down and check to see if the author thinks that's the case. And none of the sample sizes. That's correct. Is large enough. All right, so that was good. Delta. None
Took the whole page.
of them.
Or none.
All right, that's 2935.
That's crazy.
Number 35.
I don't mean that that way at all.
The president of some company believes that 30% of his firm orders come from first-time customers. A random sample of 100 orders will be used to estimate the first-time customers. Okay, so I got N equals 100. A random sample of 100. Okay. Assume the president is correct, and P is equal to 0.3. What is the sampling distribution of P bar for the study? Okay, what is the sampling distribution Okay, so on page 291, we see that P bar is the sampling unit can be approximated by the normal distribution when NP is greater than or equal to 5. So NP, 100 times 0.3 is 30, which is greater than or equal to 5. And we have to have N times 1 minus P has to be greater than or equal to 5. 100 times 0.7, which is 70, is also greater than or equal to 5. So that means that P bar can be approximated by the normal distribution. So, what was the question? Assume that the president's correct, then the sampling distribution for the study is the normal distribution. What is our other choice? The other choice is it's not normal, right? A, B. What is the probability that P bar is between 0.2 and 0.4? Okay, so the sigma of the population on page 290 is capital N minus N, but we don't know capital N. This is probably an infinite guy, so we'll go with P minus 1 minus P divided by N, 0.7. I hope I can get in there. All right, so 0.7 times, well, 0.3 times 0.7 divided by 100 square root. 0.3 times 0.7 divided by 100. Second function, square root, second function, answer. Boom. 0.0458. Okay. We want Z on the upper end. We want Z on the lower end. Okay, we want 0.3 plus or minus 0.1. 0.3 is the mean. So that'd be a 0.1. 0.1 divided by 0.0458, and we want a minus 0.1. Is it 0.1 or 0.01? It's 0.1, 30%, over 0.0458. 2.18 minus 2.18. Okay, so we want the probability of the upper limit minus the probability of the lower limit, lower Z value. 2.18, 0.9854 minus the lower limit minus 218, 0.0146. .9708. So that's our B answer. C. What is the probability the sample population will be between 0.25 and 0.35? Okay, so the C guy, the upper Z is going to be 0.05 divided by 0.0458, and the lower Z value minus 0.05 divided by 0.0458. .09 and minus 1.09. We want the probability of the upper Z guy minus the probability of the lower Z guy, and my notation is really bad. 1.09, 0.861, 0.8621 minus 0.9, 0.137, 0.1379. 0.7242, and that would be my C answer. And we come back to here. Look at this is 35. And they do a graph of the normal distribution. Isn't that lovely? Did we get 0.987 and 0.621? No, 0.7242.
Yeah,
Is that what we got? Yeah, that guy and that guy. Okay. So we're happy with that one. That was 35. 41. Number 41. We're happier when we don't have multiplicities of things, but that's okay. 41. Food Market Institute shows 17% of households spend more than $100 per week on groceries. Assume the population proportion is 0.717. And the simple random sample of 800 households will be selected from the population. Show that the sampling distribution and the sample proportion of household spendings the sample for a household spending more than $100. Okay, so we want to find that. Okay, so so what we want to do is we want to show that NP is greater than 5 and N1 minus P is greater than 5, and if that's is the case, then the distribution is a normal distribution and P bar is going to be 0.7. So that's what we're going to show first, and we have NP 800 households. But how many households? Oh, okay. So 800 times 0.17 is clearly greater than 5, and 800 times 0.83 is also greater than 5. So P bar is equal to the P guy, which is 0.17. Alright, therefore. So that's the A part. What is the probability that the random population will be between plus or minus 0.02 of the population norm? Okay. So we need to find sigma p square root of, this is on page 290, page 290. P 1 minus P divided by 800. Okay, so 0.17 times 0.83 divided by 800. Second function, square root of the answer. 0.0133. 0.0133. Okay, so that's that guy. Plus or minus 0.02. Okay, so we want to find the upper z guy. We want to find the lower z guy. 0.02, 0.0133 minus 0.02, 0.0133. $1.50 minus 1.50. So we want to find probability upper z minus probability lower z. 1.5, 0.9332 minus 0.0668. So my C answer is going to be 0.8664. Go down, go up. Did I go the right way? Go the other way. Okay. Well, C. Do it again with a sample size of 1,600. Okay. So I'm going to do it again. This is the B answer, not the C answer. So C. I want this guy again. Square root 0.17 times 0.83 divided by 1,600. .00939. Okay, we'll go with 0.00939. Okay, so the upper z, 0.2 divided by 0.00939. The lower z, minus 0.2, 0.00939. Okay. 21 point something. I bet you it's 0.02. Yeah, it's 0.02. 0.02, 0.02. 21.3. 2.13 minus 2.13. Probability of the upper z minus probability of the lower z, 2.13, 0.9834. .0166. .0998. well, whatever it is. So my C answer, 0.9668. All right. And this is 41.
41.
Okay, 41.
Seven.
We're way off now. Where's it up there? Oh, it's down here. So there's my 0.9668 and my 0.8690. Did I get 0.8690 for the B guy?
No. You have 0.8664.
0.8664. Did I get plus or minus 0.15? I think I did, didn't
You have 1.50, not 1.51.
I? Okay, so they rounded off a little bit differently.
Yeah.
Okay, so we're fine. They rounded off different than we did. 47. Where the heck is 47?
300.
Way up to 300. A firm carrying inventories different sizes contains 2,000 items. Okay, so we have 47 and 53. All right. Well, they look like about the same thing that we've been doing, so I don't see anything different in those guys. Why don't we pass out the quiz, do the quiz,